Okay. So, I mean, you might all be very familiar with this, saying this is a diode connected transistor, right, but you can see that, yeah, it is diode connected indeed, but the point is that there is negative feedback in action here, alright, where you are continuously comparing the drain current with the reference current and adjusting the gate voltage appropriately, so that the drain current is exactly equal to the reference current. Is that clear? So, this voltage therefore is Vg star, which is Vt plus square root of 2 I ref by mu n C ox W by L. Okay. So, now that we have found the Vg star, if we are on an integrated circuit, then it so turns out that if you make 1000 devices on the same IC, it turns out that the threshold voltage of all the devices is the same, at least to first order, right. It may not be what you want, but it is all the same. So, then what can you do? You can use one transistor to find the magic voltage and apply the same magic voltage to another transistor. So, this is M1, so this is I ref, this is VDD, this is M2, alright. Since M1 and M2 are exactly identical, it follows that the drain current is exactly identical, okay, and therefore the drain potential is of M2 is VDD minus I ref times RL, and as usual that RL and VDD must be chosen such that the transistor M2 operates in saturation. Okay. So, we and this current in the transistor M2 will be maintained at I ref irrespective of whether it's sunny or whether it's raining, okay, and regardless of what the threshold voltage of the transistors. Okay. So, this is an example of robustly biasing the transistor M2. So, here it just so turns out that M1 and M2 are exact clones, they are not even approximately the same like all of us, okay, alright. And so this is one way of robustly biasing the transistor. We will look at other ways, but at this point we have something, but that is not the end of it. What do we need to do? I mean, we bias the transistor, what were we trying to do? We have to make an amplifier, okay. So, now we need to convert this into a common source amplifier, and you are going to help me do it. Now, what do I do? What all should I do? So, for incremental signals, therefore, let me remind you that for incremental signals, we must as far as the amplifier is concerned, it must look like this. Okay. All right. So, I mean perhaps the Vi has some source resistance Rs. Okay. So, basically now what we should do is figure out what all needs to be done to the circuit on the left, so that as far as the incremental equivalent is concerned, it looks like the circuit on the right. Okay. So, this is like what do you call that Sunday puzzle in the newspaper, right? Find the 6 differences and make sure that for incremental signals both of the pictures look exactly the same. Okay. So, first difference between the picture on the right and the picture on the left. Pardon? Well, we need the source somewhere, okay, and the source must connect to the gate of M2. So, let us put down the source here, that is Vi, that is Rs. All right. So, how do we connect it to M2? Pardon? Putting an infinite capacitor, very good. Okay. So, certainly this connection is made, all right. Okay, then what else have we done? Okay, let's figure out what we think we are done. Let's try and see if we are done. How do we figure out if we are done? We actually find the incremental equivalent of the circuit we have on the left and actually make sure that it is the one on the right. Okay. So, what do we do? I mean, well, there is no magic here. You replace, all components by their incremental equivalent. So, let us go element by element. Current source, open circuit, all right. What comment can we make about M1? By the way, what region is M1 operating in? Saturation, because the drain and the gate are at the same potential. Okay. So, now what should I do with M1? To find the incremental equivalent, what do I do? Nothing, I just have to replace so this is let me call this I don't know, let me call this gate voltage G. So, this is G. Then what should I do in the incremental equivalent? So, this is small Vg. So, that is Vg. What should I do? So, this current is what? Gm times Vg, very good. Okay. So, what should I do now? Short circuit the gate and the drain, very good, all right. Then what happens to the infinite capacitor? Short circuit. What happens to Rs? Remains there, very good. This is Vi, correct? All right. What do we do with M2? Well, that is also Gm times Vg. Then RL, what happens to the other end of RL? Grounded. Okay. All right. So, now if you look at the small signal equivalent that we wanted and what we have, what do you see? Is there any difference? What is the difference? Yeah, okay. So, by the way, before you go there, can somebody take a look at this and simplify matters? So, the voltage across this current source is Vg and the current being drawn is Gm times Vg. So, as far as that node is concerned, to the left of that green line, it's indistinguishable from a resistance of value 1 over Gm. Okay. So, all right, 1 over Gm. Okay. All right. So, what is the small Vg therefore? It is nothing but Vi, so basically Vg is nothing but Vi times 1 over 1 plus Gm times Rs. Okay. So, is Gm going to be a large number or a small number? We want a lot of gain, correct? So, what comment can we make? Yeah, so what does it mean? What happens to Vg? I mean, Vg will be a small fraction of Vi, okay, But ideally what do we want there? We want the whole of Vi, not just a small fraction, right? There is no point in attenuating the signal first and then amplifying it later. So clearly the problem is, so do we have a problem or we don't have a problem? We have a problem. Okay. So how do we solve the problem? There are multiple ways of doing it. The bottom line is, okay, what is the root cause? This connection is the root cause, right? So what do we do? So one way of fixing the problem, basically the point is incremental current is flowing, in that connection. So for incremental signals, we should break that connection. Does it make sense? Okay, so how do you break the connection? Do you want to break it for DC also? No. Why? If you break it for DC, what happens? There is no bias, right? So basically this voltage must be the same as the gate voltage of M1 must be the same as the gate voltage of M2, correct? As far as the operating point is concerned, right? You must only remove that connection between M1's gate and Vg for incremental signals. So one way of doing it therefore is, what is a short for DC but open for incremental signals? An inductor, an infinite inductor, right? So one way of doing this is to put an inductor like that. Now what comment can you make? Of course we know that inductors are bulky, correct? Okay, and is there something else that we can do? Yeah, so basically remember that the inductor is not carrying any current anyway in this particular circuit. So instead of putting an inductor, you can put a resistor RB, right? What is the, and what comment can you make about RB? Compared to what? So one way of doing it is to basically put RB much greater than RS, okay, in which case in the incremental equivalent what happens? So this becomes RB, and therefore since RB is much larger than RS, Vg will be approximately equal to Vi, and the output voltage will be approximately or very close to incrementally minus Gm RL times Vi. So this is another example of a common source amplifier, and when you compare it with the earlier version that we had, you can see that it looks very different, but it is essentially doing the same thing. Okay. Now, can somebody comment on signal swing, the swing limits? What comment can we make? Which of the two transistors you think will influence the maximum input we can put in before bad things happen to the output? There are two devices. So as per our discussion in the last class, we have to find the swing limits for each transistor individually and find the minima, and then find the minima of the minima, right? So it basically is seems like a very painful affair, but staring at the circuit, right, what comment can we make about the incremental swing here at that node? What is the incremental voltage at that node? Yeah, if RB is very large, then the incremental voltage at the gate is 0. So what comment can you make about the incremental current in M1? There is no current. So so incremental current in M1 is 0. The incremental gate voltage at of M1 is also 0. So what comment can you make about its influence on the swing? is no influence at all, right. So, I mean, looking at the circuit itself, you should be able to say that I mean, as far as swing limits are concerned, M1 basically is completely irrelevant, right. It's only M2 that makes the call, correct. I mean, in other words, whatever amplitude you put in there, this voltage is not changing, and this therefore this current is not changing. So, the it does not matter how large that Vi is, M1 is always going to be in saturation and carrying a current Iref, all right. So, it is only M2 swing that you have to worry about, and that you can do using the usual formulas, that the approach that we discussed yesterday, right. Just to illustrate that, when you see a complicated circuit as we discussed yesterday, I mean, you do not have to, while it is true that, in principle you have to find the limits for all transistors and take the least of all of them, most of the time you will be able to see directly that many of the transistors do not contribute to these limits at all, and it makes no sense to sit and analyze the limits for those transistors, right. Is this clear? All right. Now, so this is basically this circuit is, as you all very well know, is called the current mirror. And if you want to make, and it's not only used to make copies of the same current. If you want, for example, 4 times Iref, what do you think you should do? Oh, well, it's pretty straightforward, right. I'll make 4 copies of the transistor, and since all these transistors are identical, the current flowing in this leg is basically 4 times Iref. All right. Okay. Now let's now, but sometimes when people are building discrete circuits, all right, where you do not have this luxury of having multiple identical transistors. Let us say you only have one transistor, okay, and you want to make a common source amplifier, but you want to bias it such that the current is equal to Iref in a robust fashion. So, we basically say, okay, this is VDD, this is Iref, and we have already seen that feeding the drain voltage back to the gate stabilizes the current, so that the drain current is equal to Iref. Okay. Now, as far as the common source amplifier is concerned, we want an incremental equivalent which looks like this. So, now the question is, what can we do to the circuit on the left so that it basically behaves like the circuit on the right for incremental signals, correct. Again, it is pretty much find the 6 differences and then do the needful, right. So, what all are the differences that you see from the on the what is there in the circuit on the right that is not there on the left? Source, okay, well, that is easy. Vi, that is the source, okay. So, how do I hook it to the gate? Large capacitor, Very good. We need the load resistor. So, what do we do about the load? Okay, very good. So, I put a big capacitor, and remember that we already know how to calculate these large capacitor values. Does it make sense, people? All right. So, what else? So, clearly this is in place, this is in place, the transistor source is grounded, the drain is connected to RL, source is connected to the gate. All right. What else? Are we done? What is the difference? I mean, if we draw the incremental equivalent of the circuit that we have, will we get the circuit on the right? No. What will we, what is the problem? In the basic circuit, basically, I mean, in the real circuit, the gate and the drain are shorted, whereas they should be open in the incremental network. So, what do you think we could do? We can do multiple things. What do you think we could do? Yeah, well, one way of doing it is to basically say, okay, I am going to put a infinite inductor, all right, and that that basically is a short for quiescent signals and an open for incremental signals. That basically is something that will work, but it's not terribly practical because, well, the size of the inductor has to be very large, which makes it very bulky. So, what comment can we make? Any suggestion? Well, you put a high value of resistor. Okay. All right. So, now what is the meaning of so Rx must be large, so the question is large compared to, okay. So, one way of doing it is to basically say that, well, you have an incremental network, right? What is the incremental equivalent now? You have an Rx there, correct, and you find the relationship between VO and Vi, correct. It will evidently it will depend on Rx, and as Rx tends to infinity, the expression will tend to, if Rx becomes infinite, what will the gain, incremental gain of the network tend to? Minus GMR, right. So, of course, if Rx is not infinite, then it will not, I mean, it will deviate from that. You have to figure out, what Rx must be large compared to, in order that the gain does not deviate much from minus GMR. Okay. So, one is you can do the math, right. Intuitively, what do you think that that Rx, when you say large Rx, it must be large with respect to what? Intuitively, Rs. Okay, let me give you a hint. All right. What comment can you make about the signal? I mean, signal swing here versus here at the drain. If the amplifier is working properly, what comment can you make about the gate swing versus the drain swing? The drain must be swinging a lot more, correct. So, if the drain is swinging a lot more and the gate is not swinging very much, right, for all practical purposes, what comment can you make about the current flowing through Rx? Vg is almost 0, man, compared to, Vg is only a small fraction of the drain potential, correct. So, what comment can we make about the current flowing through Rx? Roughly Vd by Rx. What is the current flowing through RL? Vd by RL, correct. So, so now can you tell me what Rx, when you say a large Rx, you want all the incremental drain current to flow through RL, right, and the voltage across Rx and the voltage across RL is roughly the same, correct. If you have a large gain, correct, the gate voltage is very small compared to the drain voltage. So, the voltage across Rx, right, which is the difference between this node and this node, right, is almost the same as the difference voltage across RL, which is the difference between the output, the drain and the ground, correct. So, the current flowing through Rx, so if Rx and RL are comparable, then the current flowing through both of them will be comparable. That basically means that the current that the drain, the transistor is pumping out is basically only a part of it is flowing through R. So, Rx must be very large, means what? Therefore, what does it mean therefore? Rx must be, this notion of large must be, is basically much larger than R. This way, no current is lost in Rx. Does it make sense, folks? All right. So, I mean, this is therefore yet another common source amplifier, all right, which again, as you can see, looks very different from the other two amplifiers that we have seen, okay. But as far as the incremental circuit is concerned, it is exactly the same.